Okay, kids, it's late. This is Polynomial Functions, and my cat just attacked my leg. So, I could very well have to pause this. I may not make my midnight deadline in the end because the cat's kind of lost her mind and is still trying to attack me, and it alternates between cute and funny and ow. So, let's jump in and let's talk polynomial functions. Okay, vocabulary. Yes, you need to know it all. A monomial is a real number, a variable, or a product of real numbers and one or more variables with whole number exponents. So, a couple of examples of monomials. Well, 3 is a monomial, x is a monomial, 3x, 3xy, 3x squared y cubed. These are all monomials. And that's because they have one term. One term, one term, one term, one term, one term. The degree of a monomial in one variable. So we're not going to be talking about the degree of something like this. The degree of a monomial in one variable is the exponent of the variable. So the degree of 3 would be no variable, 0. Degree of x would be 1 because it's x to the first. Same thing here. Again, we're not talking about the degree of monomials of more than one variable. If I had 3x cubed, that would have a degree of 3. Polynomial. Monomials are polynomials, kind of like squares or rectangles. So a monomial is a polynomial or a sum of monomials. So that would be like 3x squared plus 2x. Okay? The degree of a polynomial in one variable is the greatest degree among its monomial terms. So if I think about this polynomial here, this has degree 2, this has degree 1. So overall, the degree of this particular polynomial is 2. We don't add them together between terms. So this is something you're going to have to commit to memory because you're going to be using this in this section. A polynomial with variable x defines a polynomial function, and we can graph that. The degree of the polynomial function is the same as the degree of the polynomial. Okay, more vocabulary. Yes, again, yes, you have to know this stuff. You name using degree. So 0 degree constant, 1st degree linear, 2nd degree quadratic, 3rd degree cubic, 4th quartic, 5th quintic. Beyond that, you just use the number like 6th, 7th, 8th. We won't be seeing many functions at that level. This is about as high as we're going to go, is 5th degree. So they give an example, they give a number of terms. We name both with degree and number of terms. So 5 is a constant monomial. X plus 4 is a linear binomial. 4x squared is a quadratic monomial, and so on. When you want to put a polynomial in what's called standard form, you put the terms in order of descending numerical degree. So you would put your highest degree term down to your lowest. Don't be daunted by this particular strange looking, what the heck are those exponents kind of expression here. This is how we define polynomials in a real technical sense. And what's happening here is these are the coefficients of the terms. So this is the coefficient of this term, and then this is the coefficient of the next term. And we relate them by relating them to one another. And you notice you have n, and then n minus 1, and then the ellipsis shows it keeps going until you get down to degree of 1, and then 0. So standard form, descending degree. Okay, so when you graph a polynomial function, you get a curve. And you see a couple of examples on this page. And they're all of different degree. And we're going to look at how degree and leading coefficient sign determine the shape of the graph. So, the degree of polynomial affects the shape of its graph, determines the number of turning points, or places where the graph changes direction. So, the number of turning points is always going to be 1 less than the degree. So, a quartic function, like this first one, has 3 turning points, and you can see them. There's a relative minimum, a relative maximum, and another relative minimum. So 3 turning points. Degree of 2 would have 1 turning point. So you can see just the 1 vertex, and that's what we've been looking at with quadratic functions. Degree of 3, there's 2 here. It's difficult to tell The two turning points can actually be one in the same, and it's the case, as is kind of the case here. But you can also see where there's two distinct turning points that you can see. You still get the same effect, though, over here, where the turning points are one and the same, and that leads us to something called end behavior. End behavior is how it goes far to the left, far to the right, how the function moves to the left and to the right. And end behavior has to do with the leading coefficient's sign. So if the leading coefficient is positive, you have, for a function of even degree, you have up and up for your end behavior. So you'll have it'll be decreasing to start, and then at the end it'll be increasing. If your leading coefficient is negative, you have down and down for your end behavior. So that means we want to be looking at these leading coefficients. This one is a 1, this one is a negative 1. We say leading coefficient, hold on, gotta get the cat off my laptop. No ma'am. Sorry. She loves the laptop. She likes to lay on it a lot. It's probably what messed it up in the first place. Anyway, so the leading coefficient here, it's the coefficient of the degree with the term with the highest degree. When you have an odd degree, a function of odd degree, you have the leading coefficient is positive. It starts with down end behavior and ends with up end behavior. And then if your leading coefficient is negative, it's up to down. And sort of, if you think, it kind of has like a negative slope kind of thing going here, and this one kind of has a positive slope kind of thing going here. It isn't really slope, but you can see what I'm talking about. Okay, so I thought this was actually a really interesting question. Normally, if I needed to find out a relationship between a bunch of ordered pairs, between the x and the y and a bunch of ordered pairs, I use my graphing calculator. But let's look at what we would actually do if we didn't have a graphing calculator. How would I determine what kind of relationship this has? So I want to know, what's the degree of the polynomial function that generates this data, this set of ordered pairs? So what we're actually going to do is we're going to look at the differences of the y values. Okay, so let's look at this. So here are the y values. Hold on, gotta throw the cat toy. Okay, make the cat happy, she won't keep climbing on the laptop. Anyway, here are the y values. So what we're going to do is we're actually going to look at the differences between them, and we're going to find the first difference, and then we're going to find the second difference. And basically what we do is we find the differences between the y values up until they're all the same, up until they are constant, up until that difference stays the same. All right, so that's what we're going to do here. So in other words, that means taking this and saying -7 minus -1. Well, that's -6. -3 minus -7. Well, that's +4. 5 minus -3 is 8. 11 minus 5 is 6. 9 minus 11 is -2. And -7 minus 9 is -16. Now we're going to do it again. Okay, now we're going to do it again. So 4 minus -6. 4 minus -6 is 10. 8 minus 4 is 4. 6 minus 8 is -2. -2 minus 6 is -8. -16 minus -2 is -14. All right, now let's do it one more time. 4 minus 10 is -6. -2 minus 4 is -6. -8 minus -2 is, again, -6. And -14 minus -8 is -6. And so what this tells me is that because it's on the third difference that they go constant, that the differences become constant. If it's on the third difference, this is a third degree polynomial. Take some time to ponder why that might work, and we will talk a little bit more about why it would work in class. I just think that's an interesting thing to bring up because you're so used to the graphing calculator. What exactly do you do if you don't have one? Okay. Now let's take all the different things that we've just learned at this point and let's go ahead and apply them. We're going to do the graphing part in class because it is a lot easier to do when you are face-to-face there together. And I can show you how to manipulate things on your graphing calculator to make it easier. But let's do a little bit of practice just to sum up what we learned. Alrighty, so for those of you wanting to play along at home, this is in your textbook. This is page 285. And you'll find most of the examples I used today were from your textbook. So if you want, or I would prefer it this way, but if you choose not to, that's your decision. Can't be there to make you do it. But if you pause your video, try these problems, and then start it up again. But either way, I'm going to go ahead and get started. So let's look at the first one. So we have classify each polynomial by degree and number of terms. So for number 1, we got 5x cubed. So we've got one term, so that's a monomial, and the degree is 3. Degree of 3 would be cubic, so this is a cubic monomial. All right, number 2, we got 6x squared plus 4x minus 2. So we know we're looking at 3 terms, and it probably looks familiar because we just finished a whole unit of this. Please excuse the cat. She's running around the house, bouncing off of couch or chair. She's been kind of full of it tonight. Anyway, sorry. Degree of 2, 3 terms. So we did nothing but deal with these for a while as we were learning and working on and reviewing how to factor. So this is a quadratic trinomial. Okay, number 3. Write each one in standard form. So we know we have second degree, first degree, 0 degree, or quadratic, linear, and constant. Easy stuff. All right, negative 3 plus 9 would be, or 9x would be 9x minus 3. Okay. Number 5. Describe the end behavior of the graph of y equals negative 2x to the 7th minus 8x. So this is a perfect example for us to be thinking about and looking at in a video, because you don't have graphing, well, you do have graphing calculators, but you better put it down right now. I don't want you to look. I want you to know this without. I want you to think about this without graphing it. So your leading coefficient is negative, and your degree is odd. So leading coefficient is negative, and your degree is odd. So what does that tell you about your end behavior? Well, regardless of what's going on in the middle, we know that this is a negative leading coefficient. It's got to have that downhill thing going. So the end behavior on this side is going to be up, and the end behavior on this side is going to be down. Opposites because of its odd degree. Okay? 6. Can the graph of a polynomial function be a straight line? If so, give an example. Well, sure. Take number 4, for example, and tack on a y. Whoops. Sorry. There we go. Take number 4, for example, and tack on a y. Make it 9x minus 3 equals y. This is a polynomial because it's a linear binomial. So it kind of gets, to that point where you think about, well, it's a square, or it's a square, which makes it a rectangle, which makes it a rhombus, it's a square, which makes it a rhombus, which makes it a parallelogram, and it's a square, which makes it a rectangle, which makes it a parallelogram. I mean, it gets to the point where everything just it's nesting. So instead of worrying about, well, could that be a polynomial? It's kind of a silly question. So shame on Pearson. I think that's a stupid question. That's just sort of nitpicking and thinking about syntax, really. Okay, 7. Your friend claims the graph of the function y equals 4x cubed plus 4 has only one turning point. Describe the error. Well, you learned here that it's degree minus 1, right? Degree minus 1. So this has degree of 3 minus 1. Say, no, friend, you're wrong. It has 2 turning points. So I'm hoping this doesn't end up too long tonight. I'm going to go back and check the time, see if I need to go back and adjust any of my slides. But it's a good unit, easy stuff, and I will see you guys in class.